Good afternoon, everyone. Thank you for joining us today. Just as a reminder, the seminar is being recorded and is being streamed on YouTube. If you have any questions regarding today's talk, you can ask them in the chat, and I will ask them at the end of the seminar. So today's speaker is Professor Jimmy Raeder, and he will be discussing global MHD models. Professor Jimmy Raeder got his PhD from the University of Cologne in 1989. He then moved to UCLA, where he started his career as a research geophysicist. In 2003, he started as an associate professor at the University of New Hampshire, and in 2009 was promoted to professor. Jimmy has nearly 200 publications and has always worked very closely with global magnetohydrodynamic models. He is the lead developer of OpenGGCM, a open source global MHD model, which you can run at the Coordinated Community Modeling Center. Jimmy is actively involved in the space physics community, and we are delighted to have him here today to discuss global magnetohydrodynamic models.
Okay, I think it's me now. Well, thanks a lot. I mean, for the Kyle and David and everybody else involved in the seminar for inviting me. So yeah, I want to talk about global MHD. Actually, I will talk it the other way around, MHD and then global. So there are a lot of contributions from my collaborators here at UNH, and it's Kai Gemashevsky, Doug Kramer, Bashi, Beckett Tologenov, who's been here for about almost a year now. I mean, from Embry-Riddle. Also looked with Naomi Mariyama with the Ionosphere-thermosphere models, and I probably forgot a few people. I mean, there's Mei-Ching Fock is involved now with a new proposal, and we also work with the RCM folks down at Rice University. So, oops, where do I get my next? There we go. So I want to start out with the MHD itself, because I think there are quite a few misconceptions in the community, and also just to make sure everybody is on the same page here. So the MHD equations are not just basically, they are the conservation equations for the mass, momentum, energy, and magnetic flux. So they include a lot of simplifications that I will get into in a while. And so they are, but any more sophisticated plasma model would still have to obey the MHD equations. I mean, if you simplified the solutions. And the only term that doesn't fit here really the bill, I mean, is the displacement current, because that is really just dropped, not simplified or anything like that. But the displacement current is also kicked out of quite a few other models that are more sophisticated. So why do we actually deal with MHD? Well, it's not just the modeling. I mean, it is, you find these basic solutions or elementary solutions of the MHD equations virtually everywhere in space. I mean, you got the Alfvén waves, they were observed in the solar wind, I mean, decades ago, you got the magnetosonic waves there. I mean, just looking at the solar wind, you find the tangential discontinuities, you find rotational discontinuities, you find shocks, you find all kinds of surface waves like Kelvin-Helmholtz. I mean, and there's a whole list of other instabilities that are MHD based and very well described by MHD, like ballooning modes, for example, or other kinds of instability. So now the MHD equations are derived, I mean, from the Vlasov or Boltzmann equation. So the difference being that the Vlasov is collisionless and Boltzmann includes a collision term, and Maxwell's equations. Okay. Now the former ones are actually the foundations of kinetic theory. I mean, and they include the temporal and spatial scales that are really not useful for global simulations. I mean, if you really want to include all these scales, I mean, you have to go down to the Debye length. I mean, we're talking about meters, and you have to go down to the plasma frequency, which can be, I think, megahertz, right? So that's not a global scale. So you have to somehow get rid of that, So the goal is then to simplify the equations in a way that they still capture all the relevant physical processes, but at well-defined macro. And I also include mesoscales, because the macro scale is the scale of the entire system, So I need, for the Earth, I mean, that's some tens of RE, in each direction away from the Earth, But I mean, we can nowadays resolve much smaller scales, flux transfer event, Kelvin-Helmholtz waves, like little flux ropes, that are really at mesoscales, So they are already approaching the kinetic scales. Okay, now I'll go to the derivation a little bit, but not too much. I mean, this would be well, I don't know, 3 or 4 lectures to do the whole thing. And most of that is in textbooks, you know. So if you want to read it up, I mean, George Park's textbook is probably the best one, in my opinion, to do that. But we want to understand what the limitations are. So I have to discuss the derivation a little bit. So first we drop the displacement current. Okay, so that eliminates the time and spatial scales of light waves, which is fine. We don't care about the light waves and other electromagnetic waves, purely electromagnetic waves. But it also modifies the Alfvén speed. So if you really write it down with the displacement current, there's terms in there that actually limit the Alfvén speed to not getting faster than the light speed. But if you keep the displacement current and terms in there, you know that, well, if you don't have those terms, you know, the Alfvén speed is virtually unlimited. You know, b squared, or the square is b squared over rho. You know, so rho goes small, b goes large. You know, it can go. And so the Earth actually that matters, because in the near Earth region, there's a thing that we call, or some people call, the Alfvén resonator. It's basically an area or volume, I mean, extending from around a few area around the Earth, where the Alfvén speed can become very large. I mean, really approaching the light speed, you know. So, but the thing is, we basically exclude that region from global simulations for other reasons anyways, which I will give later. So we don't really care about the displacement current. However, then some codes, actually many codes, I mean, reintroduce the displacement current for purely numerical reasons. I mean, and the reason is that you want to limit the time step, you know. So if you had an Alfvén speed that becomes too large, you know, and talk about that in a little bit, you will have to limit your time step. In other words, it becomes very expensive to compute. So you want to fiddle with that a little bit, and you can do that by doing the so-called Boris correction, which means you basically reintroduce the displacement current or some variant thereof, I mean, to limit the largest possible speed in the system, you know. So we know the largest speeds that we care about are a few thousand kilometers per second, you know. So we put in a c, a light speed that is of that value, you know, and so nothing can go faster than that, and that makes the computer happy. The plasma equations then are basically the first 3 moment equations of the Vlasov-Boltzmann equation. Now, if you want to see the derivation of that, I think the authoritative paper here is Barakat and Schank from 1982, I think in Physics of Plasmas, you know, where they developed the entire hierarchy of the moment equations. I mean, much higher than MHD. So MHD is only 5 moments, you know. I mean, then there's a 10 moment, a 13 moment, a 20 moment, and whatnot hierarchy of equations. I mean, in MHD, it's truncated. I'll explain it in a minute. Now, the other thing that one does in MHD, which is important, I mean, the ions and the electrons are basically thrown together in the same bucket. And then one can make the assumption, which is a pretty good one, that the terms that are scaling like the mass ratio, I mean, ME over MI, which is a very small number, you know, it can be thrown out. And we also assume that there is a quasi-neutrality. So that doesn't mean there is a net charge density. It just means that the density of the electrons and ions are very, very close. And even if there is a static electric field that requires a fairly large charge density, you know, the difference between the 2 densities here would be still very, very small. So, okay, so these assumptions together, they eliminate basically all processes that depend on charge separation, like plasma oscillations, plasma frequency, Debye length, and things like that. So now when you look at the equations that come out of that, you know, continuity equation is very straightforward. You know, the rate of change of the density, mass density, is the divergence of the mass flux, rho v. Now the momentum equation, I mean, it can be written in different ways. One can also write it as an equation for v instead of rho v, which is the momentum. But for numerical reasons, it's always advisable to write it this way, where you have on the right side a divergence of some flux. Okay, so this flux includes the inertia, it includes the pressure, and includes the electromagnetic forces here. Now these can be written in a different way, you know, so you have the divergence of BB and all that. You can really rewrite that and it becomes J cross B. So that's the way it's often written, and it's more convenient and it's more easy to interpret. So they're all in divergence form for numerical treatment. We also assume that the pressure is isotropic here. So that's already a fairly significant simplification. in many regions of the magnetosphere, the pressure is actually the distribution functions are pretty symmetric, and that's not a bad assumption, but it's certainly not true everywhere. I mean, for example, at the magnetopause, when you have a northward IMF, you get a or even just downstream of the bow shock, you get an anisotropy. You can have anisotropies in the tail. So that's probably a pretty heavy approximation. Now, unfortunately, the next approximation of what can do is the Chu-Goldberger low, CGL, where you have an anisotropic pressure, a pressure parallel and perpendicular to the field, is by itself not necessarily a good one either, because it doesn't really include the processes that limit that anisotropy. You just get anisotropies that are way too large. There's also no source terms in here. So in the magnetosphere, we don't have many sources. I mean, there's some sources in the inner magnetosphere where you actually charge exchange with a neutral halo with the exosphere. But other than that, you have very little. I mean, it's different in other settings. I mean, if you go in the heliosphere, you got the charge exchange with the or ionization of interstellar neutrals, with really mass load and momentum load, and also inject energy into the whole system. But the magnetosphere, usually we can completely neglect that. Okay, the energy equation now is a little bit more complicated. So there's different ways to write it. One can also write it just as an equation for the pressure, but for numerical reasons, it's advisable to write it in divergence form. So the rate of change of it's not the simple. I mean, it's either the total energy, where you include the plasma pressure, the inertia, and the kinetic energy and the magnetic energy, or you'll leave the magnetic energy out. So these are two popular versions of the energy equation. Now, the first one is certainly the more. I mean, they're all equivalent mathematically. You can just go from one to the other. That's not a big deal. But for numerical reasons, it's much better to have the full divergence form like the one and above. But it gives you a little trouble sometimes, and especially when you have a low beta plasma, because then you have to calculate the pressure out of the difference between U and B squared. So then those are two very big numbers. And if you take the difference between two very big numbers, you introduce a large error, and that can give you a negative pressure. So one tries to avoid that. And so compromise is to use the energy equation in a form here where only the gas dynamic part is actually in a conservative form, in divergence form. And the work done by the fields is then J dot E. I mean, it really looks like the Poynting equation, Poynting's theorem, and it basically is Poynting's theorem, just extended by the gas part. It also has an advantage that it actually makes clear that the magnetic field does not do any work. Okay, so a magnetic field cannot do work on a plasma, simply because the Lorentz force is always perpendicular to the magnetic field, so that you get the triple product that always has to be zero. So it's really this term. And now this term is, I think, often misinterpreted. Often people call this dissipation. It is not dissipation. Actually, it can be completely adiabatic. So it's really only the work done by the fields on the plasma and vice versa, depending on the sign. And so the adiabatic part of that is simply that you compress or expand the plasma, or that you accelerate the plasma. So you can rewrite this, and I probably should have done this here. And J dot E can be written as the velocity dot, I have to go back. The velocity dotted with J cross B. So it's the velocity times the J cross B force, and that is just the rate of work done on the plasma. Okay, so now I also included in the equation a quantity I named Q here, which is the heat flux. So I mean, in the full momentum in the full hierarchy of the equations, it's actually not it's a rank 3 tensor. So I mean, a simplified version would be of heat flux. Now, why is it there? It comes from the hierarchy of the moment equations. And so we have to somewhat deal with that. And the simplest way to deal with it is just setting it to 0. So assuming there is no heat flux. There's reasonable reasons to do that. Not really perfect, but I mean, that is where we have to what we call either truncation or closure of the equations. So even if we carried an equation for the heat flux, and there are codes now that actually do that, then they have to close it at the next higher level, which would be a tensor of 4th rank, and then and so on. So at some point one has to close it. So I think the justification to do that is pretty much in the proof is in the pudding. It works. Or one can argue that the heat flux would actually be zero when you have well, you don't even have to have a Maxwellian. I mean, you only have to have a symmetric distribution, one that is just f of v. I mean, where v is not a vector, it's just the magnitude of the velocity. So then the heat flux becomes zero. I mean, if you write down the moment for the heat flux, you can see that that becomes zero. So yeah, so whenever everything is Maxwellian, or at least nice distributions that are not skewed, I mean, Q would be naturally zero. So that's not that big a deal. So if I summarize all that, what is really important, I mean, there are other limitations that I didn't really go into, but I mean, what's really important is that the spatial scale is limited at the gyro radius or the ion skin depth. I mean, for a beta equals 1 plasma, they're the same. Now, in the magnetosphere, these are typically less than about 100 kilometers. So that is less than what we can resolve anyway. So MHD is quite appropriate, for numerical simulations of the magnetosphere. Now, correspondingly, the MHD temporal scale limit is the gyro period. They don't have any explicit terms in there that make gyration. So that falls out. And again, gyro period is typically of the order of a second or so. I mean, for particles in the magnetosphere, which is much smaller than the timescales we are interested in general. Yeah, I said that already. The heat flux has to be zero. I mean, this is also implies that we conserve specific entropy. I mean, that is P over O to the gamma. And it is consistent with a symmetric distribution function. Now, if you have a symmetric distribution function that is not a Maxwellian, you actually get higher moment equations, but they're not coupled to the lower moment, so you don't have to worry about them. Now, this is also not always understood. I mean, there is actually a static electric field in the equations. Although we don't have the charge density explicitly in there, I mean, it is there. And you can calculate the charge density anytime you want to do that, just from Gauss law. Just take the electric field, I mean, take the divergence of that, gives you a charge density. That's why it's not called neutrality. We don't assume neutrality, we assume quasi-neutrality. That's a just very small difference, but there is a charge density there. And if I remember correctly, there was a paper recently by Joe Borowski, I mean, who discussed this in great detail as it applies to the solar wind. Then also, it should be totally clear. I mean, a magnetic field does not work on any particles. It does not. Does not explicitly appear in the energy equation. So, if you write it the right way, I mean, only the derivatives of B are in there. So and that's consistent with the Poynting theorem. Now, this I should make that red, but I come back to that anyways. The ideal MHD equations, the way I wrote them down, do not permit any reconnection. Okay. But as I will explain in a minute, I mean, there's no stable numerical method that actually solves the ideal MHD equations without introducing some sort of a numerical resistivity, which then gives you a pathway to reconnection. Let's put it that way. So a little bit on the solutions. I mean, all the codes that are around, I mean, the major codes, I mean, use some form of finite difference or finite volume methods. Now, yeah. Have to define a grid. That's always the first thing you have to do, and I will not go into the details. And that's actually where the codes really differ. So the OpenGCM, my code uses a stretched Cartesian grid, so it's still nicely perpendicular. But in each coordinate direction, it's stretched. Michigan code uses what they call a block adaptive grid, which is little blocks of 8 by 8 by 8 cells, of various sizes that are overlapping. And the LFM code, or as it's called, the newer version, Gamera, they're matching a spherical and cylindrical grid because that matches very well the size or the shape of the magnetosphere. So you try. I mean, they really try to get away. I mean, with at least the least number of cells, to compute. But they pay the cost. It's always a compromise here. They have to pay the cost that it's much more complex. Now, the conservation, I wrote down the equations in conservation form, which means there's a rate of change of a variable equals the divergence of something, which can be integrated and then use the mathematical Gauss law to make that into an integral equation. And so that means that mass, momentum, energy are conserved, and that can be done numerically exactly if one places the variables right. So one has cells here. This is in 2D. At the cell center, that's where you place the variable. I mean, the energy density, the density, momentum, and so on. And then you put the associated fluxes on the centers of the faces, and then you can easily show that this whatever goes out from one cell has to go into the other cell, and that guarantees you that you really conserve the variable, I mean, on a global scale, except of course for the boundaries where stuff can flow in and out. And so you can write it, I mean, without considering the time integration at this point, I mean, just as the simple difference of fluxes here, so I mean, but now these fluxes have to be what's called limited. Again, that would be a whole lecture at least, to provide a non-oscillatory and stable solution. It may seem that it's simple to calculate those, I mean, but it's actually not. I mean, that's a sort of an art how to do that. But when you do this and you analyze your, that's what numerical analysis is all about, yet another lecture. You'll find that you're actually not really solving the differential equation that you try to solve. You solve it and you get error terms. And these error terms, you can write them out. They're proportional to the higher derivatives of the solution. And for most schemes are second order accurate, so they have an error term. The first error term and the largest one is one that is proportional to the square of the grid spacing, and that's why it's called second order. And it is proportional to some second derivative. So that means it is proportional to a diffusion term. And then the next one is an odd derivative. So that actually introduces dispersion. And then the higher order terms, Okay, so there are higher order schemes out there, so which actually make the A1 and B1 0, for example, but then you still have the A2 and B2 and so on. So there's virtually no way to get rid of all these errors. Not virtually, there is no way to get rid of all these error terms. Okay. So yeah, what you want to do is you want to calculate the fluxes in a way that makes these error terms as small as possible, and you have to require, I mean, a balance between accuracy, stability, dispersion, and diffusion. So there is one scheme that is actually possible where you can kill all the even derivatives, so you get rid of all kinds of diffusion. Well, unfortunately, that's the leapfrog scheme, but unfortunately, that is very dispersive, so you get oscillations that are not real, and that blow your solution up eventually, So Joachim Bern's older codes, I mean, were actually that. So most schemes are second order accurate, so that means that the leading term is actually this term. And most codes also employ an explicit time integration scheme, so I'm not going to go into time integration here. And that limits the stable time step. So that means you cannot make your time step as large as you want, but you're limited to that. It's a so-called Courant-Levy-Friedrichs CFL, Courant-Friedrichs-Levy criterion. And so basically the time step has to be proportional to the smallest grid size here. And so that means that if you want to go to a better resolved grid, so let's say you want to halve the grid size, the cost that you associated with that is 16 times the computational cost. So it becomes very expensive to get up with the grids, So the only good news here is that the power of computers actually grows exponentially, at least up to now, in time. So and an exponential always grows faster than any power. So I mean, we're making quite some strides here. Okay, one more thing about the numerical solution, actually two more things, is the conservation of magnetic flux, which is not so trivial. And that problem was only really solved, I mean, about, I think the paper was in '88 by some astrophysicist. And so, yeah, Faraday's law and Maxwell's law just require that div B equals 0. In other words, all the magnetic field lines have to be closed, or end on a boundary. I mean, they cannot end somewhere in space, and so that has to be conserved. But what is more important actually is that Faraday's law ensures that the div B doesn't change. So if you take the divergence of dB over dt, that is the same as the d over dt of the divergence of B. So the rate of change of the divergence is the divergence of the curl, that has to be 0. So in other words, whatever div B is there, Faraday's law will carry that on. If it's 0 at the beginning, it will be 0 for all times. So what's really difficult to do numerically is to make it, it's not so difficult to make it div B equals 0 at the beginning, but I mean, it's difficult to make sure it doesn't grow. And so that can be changed achieved with this what's called the constraint transport algorithm that was just referred to. I mean, an ADA was published. I mean, it's later people found out that other people, I mean, a Japanese guy published it in an obscure journal 20 years earlier already. So that's why it's actually also called the Yi grid right now. And so the trick to do here is that one places has a staggered grid. So if this is a cell, I mean, one places the X component of magnetic field on the X phase, the Y on the Y phase, the Z on the middle of the Z phase, and the electric field components that are coming in where you need to curl off to advance the magnetic field, you paste them on the centers of the edges. And then you can write the curl with Stokes' theorem as a line integral around the phase. And you see the elements of the line integral here. I mean, these arrows, they always occur twice. You know, they occur twice, once on this phase and one on that phase and so on. And you have them all up, I mean, they become zero. So that means that the total flux, the integrated flux over the entire cell that goes in and out of the cell does not change. Okay, so the rate of change is zero, you know, numerically, strict numerically. So most codes use that. Not all of them do. If you don't do it, you have to do something else, and whatever else you do is usually not so perfect. There's also variations now of the method. I mean, that don't require the staggered grid, but then you get it's always trade-offs. Then you have to have larger stencils, you know, I mean, finite different stencils. Okay. Now I filed that under numerical solution here, and that is the process of reconnection. I told you already that you cannot have reconnection if it's really ideal MHD. And of course, reconnection is important. I mean, everywhere, you know, in the corona and the heliosphere and the magnetosphere, you know, in all kinds of astrophysical settings. And what reconnection requires is the existence of a localized parallel electric field. Okay. That field can be caused by various processes. So it could be some sort of resistivity, it could be electron inertia, or it could be the divergence of the electron pressure tensor, for example. So the MMS mission is actually entirely dedicated to pretty much find that out. And I think they have put their finger already definitely on the electron pressure tensor. But as always with missions, you know, you have to be lucky sometimes to get the right measurement at the right time, and it's not always definitive. So I think it's still a pretty much open thing which dominates where. And in my personal opinion, it probably depends on what parameters you're in. You know, corona is probably a bit different from the magnetosphere, and which is probably different from the photosphere, and which is probably different from, let's say, the coma of a comet, where you actually have resistivity due to collisions. So in MHD codes, the only way you can actually make that paraelectric field, you know, is some sort of resistivity. So I just explained to you that numerical solutions always include some sort of a numerical diffusion. Okay, so diffusion for the Faraday's equation is, of course, resistivity. So that means since every practical MHD code has numerical resistivity, all just such codes produce reconnection. That's just a fact. I'm not aware of any code that does not produce reconnection and is stable. So sometimes people add a little bit of extra resistivity. Then, I mean, there is a theory of how resistivity can arise in a collisionless plasma, and then it's called anomalous resistivity. So sometimes you can add that. I mean, actually in OpenGCM, we do add that, but it's not really critical. I mean, even without that, I mean, you will get reconnection. So the questions then are, does it really matter what produces the paraelectric field? And I think the conclusion is not really. And so the MHD scales are much larger than the electron scale. So if you look at a single cell, you know, what actually produces that paraelectric field in the cell, you know, MHD could not distinguish that, you know, what actually produces that. So as long as the magnitude and the extent of that paraelectric field are roughly correct. Okay, now we have some theory, I mean, years and years of theory about reconnection, you know, and that tells us that resistivity, actually, if it's resistive reconnection, that the value of the resistivity or dependence on resistivity is fairly weak. So that's usually a log term or some small power fraction of, I mean, smaller than 1 power. So is it in the right location? Well, in MHD, the paraelectric field is strongest where the currents are the strongest because they're proportional to the currents. And so, but that's also usually where the kinetic effects maximize, you know, I mean, to get that skewed electron distribution function, you know, you have to have the current sheet, you know, that's in uniform plasma, you know, that just doesn't happen. So I would say a check, you know, here. Now, is the reconnection rate correct? Okay, again, theory would indicate so, but in the magnetosphere, we also have, that's the good thing about the magnetosphere, as opposed to the corona, for example, we can actually measure the reconnection rate really well, the global reconnection rate. It's just this cross-polar cap potential. I mean, because that field, I mean, you can make a Faraday loop, and show that that is the reconnection rate essentially, And so in the CPCP, I mean, the cross-polar cap potential is pretty well measured. I mean, not directly. I mean, it's always somewhat indirect. I mean, either through radars or to satellites and all that. But the codes, what we produce is always within the ballpark. And within the ballpark, I would have said 20 years ago, a factor 2, nowadays, probably within 30%. So our reconnection rates cannot be that wrong. Now, one can have a much, much longer discussion here, and so Jim Drake addressed that a little bit last week, whether it's really the local conditions that determine what the reconnection rate is, or whether it's actually the boundary conditions. I mean, that's also an argument that goes back many decades, So, but I think for our purposes, it really doesn't matter, because the proof is in the pudding. We pretty much get it right. Okay, then finally, does the reconnection in MHD occurs at the right location and the right time? So now that is much harder to address. First of all, we don't have so much measurements. It's difficult to measure where I mean, we have only single spacecraft, I mean, so they often measure just the result of reconnection, but not exactly where it happens and what the extent of the next line is, for example. And MHD codes, I mean, yeah, what we find is thin current sheets begin to reconnect very quickly. Whenever you have a thin current sheet, I mean, it will reconnect. I mean, there's nothing you can do against that, almost nothing. Now, nature may be a little bit different. I mean, and what always concerned me was the so-called CEDAR-9 event. I mean, long time ago, when they had the coordinated data analysis workshops, and this was the event number 9, which was really, really heavily analyzed. And because it actually had 2 spacecraft, IC1 and 2, bracketing an enormous current sheet, and the current sheet was stable for 15 minutes, and then eventually it exploded. Okay, so an MHD code would probably not do that. I mean, it would probably start reconnecting earlier. So I would say that's not really clear. But to summarize that, I think there's an analogy which actually holds pretty well. And that is boundary layers in fluid flow, in viscous flows. I mean, an airplane cannot fly without viscosity. But the value of viscosity really doesn't matter that much. I mean, actually, air has very little viscosity, and airplanes can fly. And you can show clearly, analytically, that if there's no viscosity, an airplane would have to fall out of the sky. So I think the reconnection is similar to that. Yeah, you need some resistivity or something that breaks the frozen-in condition, but you doesn't have to be very much. Okay. One final thing with reconnection, which I think is often misquoted. So there was in 2001, GEM had what they called the Reconnection Challenge. So a bunch of people led by Byrne and ran different codes. I mean, just reconnection in a box. I mean, a Harris sheet, breakup, and looked at, I mean, what the reconnection rates were. And the result is summarized in their famous figure here. So where they have a full particle code, that is the solid line. They have a hybrid code, which is the dotted line. They have a Hall MHD code, which is the dashed line. And they have an MHD, which is the dot dashed line. And it is so evident here, apparently, that MHD doesn't do right? Okay, so, and the upshot of that paper was, yeah, you have to have the Hall term in your equations, I mean, to get the right reconnection rate. However, there was a paper right after that by Antonius Otto. And what Antonius did is he took MHD equations and put in different types of resistivity, and the Hall current and no Hall current. Okay, so what does he find? Yeah, a uniform resistivity like they did here in that simulation, I mean, in the Byrne paper, yeah, gives you a fairly low reconnection rate. If you have a constant resistivity, but the Hall term, you get the dashed line here, so which is a bit faster, but still not quite that fast. If you do Hall MHD together with a current dependent, so this is hard to read, this means res of resistivity function of a current, you get the fastest rates, okay? And then what you can almost not see at all here is that MHD without the Hall term, but a current dependent resistivity also gives you fast reconnection. So now what we actually have in practice in our codes is a current dependent resistivity. So that's why I think is the reason why we get the reconnections rate quite right. And John Dorelli, long time ago, I mean, did actually experiments with the OpenGCM where he used a constant resistivity, and yeah, and he found low reconnection rates and flux pileup and everything that's associated with that. So I think I mean in a natural way we actually get it right. Okay. So I think I have to speed up now a little bit. So, well, if you just want to do simulations, MHD simulations in 3D, you don't have to write a code anymore these days. I mean, I think the MHD code wars are over. I mean, there are packages out there, Zeus, Athena, Flash. And the one that I really like is Pluto. Can download it on the web. You know, it's very efficient. It's parallelized. I mean, and the nice thing about Pluto is it allows you to choose pretty much any algorithm that has ever been developed to do simulations, you know, do MHD simulations, you know, so you can actually test one algorithm against another and see how things depend on algorithms. But that does not give you a magnetosphere, you know, so because the magnetosphere is only there because you have the Earth in the middle, and the Earth has its own magnetic field, so you have the solar wind blowing onto that. And so what we do, and pretty much every code does, is to make a shell here between the Earth and the actual MHD domain where we do not solve the MHD equations, we just map stuff back and forth. And so at a minimum, you need an equation for the ionosphere potential that closes the field line currents that are generated in the ionosphere. So fold down currents are the J parallel. Sine I is just the sign of the inclination, just a geometric vector. And then you have a potential equation, which you usually solve on a 2D shell, I mean, around the Earth. And that requires the conductance tensor, you know. So this is not MHD in the ionosphere. This is highly collisional plasma. So you have finite conductance there, and not only that, it is anisotropic because you have a Hall and a Petersen conductance. So I will not go into the details here. I mean, that is also well documented. Now, no, this should read magnetosphere. The field line currents come from the magnetosphere, the conductance tensor. Yeah, the old models, I mean, the old days, people just took a uniform conductance, you know, then we found out that's not good. I mean, there are some empirical models for that. That's not really good either. And so these days, so I think what pretty much every model does is we have it coupled to a ionosphere-thermosphere model. So we currently in OpenGCM, we have CTIM, that's the coupled thermosphere-ionosphere model from NOAA, from Tim Fuller-Rowell. And we are moving now on to WAM-IPE, which is the whole atmosphere model coupled with the ionosphere plasma for the electrodynamics model, which is a newer version for the. So the WAM is basically the neutrals and the IPE is the charged particles, okay, for the ionosphere. So what you need then is you need a model that somehow tells you how much electrons precipitate, because that's an important input for the ionosphere models. And so we typically do this with some sort of parameterizations from where we, based on field line currents and plasma parameters, the magnetosphere, we calculate how many and how energetic the particles are that precipitate. And it works reasonably well. You can compare that directly to aurora. So I will show you something in a minute. Don't have that much time. And then there's a feedback from the ionosphere to the thermosphere, to the magnetosphere, you know, which is basically through the electric field. So you calculate an electric field down here that gives you an electric field and velocity boundary conditions on the boundary. So, and some codes nowadays also include outflow, you know, plasma that actually comes out of the magnetosphere, of the ionosphere and flows into the magnetosphere. So if you put this all together, and this is, I'm speaking for OpenGCM now, but pretty much all the models have a similar flow diagram, you know. So you have an MHD core where you solve the MHD equations. You have some module that maps everything to the ionosphere. You have a ionosphere model where you solve the equations in the ionosphere, and you have a potential solver, so that sometimes comes together. Now we also have something that I haven't really talked about. It's fairly new. In the inner magnetosphere, drift physics, MHD isn't so good. There's drift physics that produces the ring current. All that, for that we need to trace field lines, calculate field line or flux tube volume. We feed that into a submodel, the Rice convection model, which has a long heritage from Rice University, which then also produces density and pressure, which in the inner magnetosphere overrides more or less the MHD solution because it's considered the more correct ones. So the whole thing is parallelized. I mean, runs, between, well, you can run something on 8 cores, and you can also run on 32,000 cores. The grids range from 1 million to 1 billion cells. Typically, a small run, 10 to the 7 cells and 500 cores runs much faster than real time on today's computers. And with the stretch Cartesian grids, you can go down to 50-kilometer resolution, which is roughly C over omega pi. So that's where MHD starts to break down, but it sometimes still makes sense to run such high resolution, I mean, just to get the diffusion term smaller, they're proportional to delta x squared, as I explained. So you can run it at CCMC for yourself if you want, and we are presently working on replacing CTIM, which replacing the RCM, or make it another option, I mean, to run Goddard's matching Fox-Simi model, I mean, which also includes the radiation belts. I mean, goes to much higher energies than RCM, and it includes pitch angles. And CTIM will be replaced, as I said already, with 1MPE. Okay, some examples. So this is really old, but it tells you some very basic physics. Okay, so they're just two simulations, and the only difference here is the conductance of them in the ionosphere. So in the top model, I mean, there's some self-consistent model for the ionosphere, so that's what you should use if you want to be close to reality. And the bottom figure here, I just cranked up the conductance artificially high, 50 Siemens. That is almost as infinite, at least an order of magnitude higher than it's there. And you see there's a very distinct difference, and the magnetopause on the day side moves in. So there's reconnection happening here, and there's reconnection happening here. And so this opens up field lines, they convect into the night side, and then they should go back in the third dimension. But if you have a very high conductance here, you basically suppress convection. Okay, so all the flux piles up in the night side and doesn't go back to the day side. So which tells us, and there's the opposite, which I don't show here, which looks pretty much similar to this. It's the opposite is where you have a zero conductance. That would be, for example, Mercury. Has magnetosphere but no ionosphere, so there's zero conductance. So the Earth is somewhere in between, and so what this tells us is that the ionosphere feedback is actually quite critical. You shouldn't do simulations, I mean, without the feedback. I mean, very early ones did that. I mean, and they weren't so good. So a few years ago, a student of mine did that a little bit more detailed, so looked for more subtle effects. So what he did was just changing the electron precipitation, which we, as I said, we parameterized that. So we have a parameter alpha in there, which when it's very small, it produces less precipitation and less energetic precipitation. For alpha equals 10, it produces more. So this is a real event. And so you see the comparison here when you have very high. So this is a magnetopause standoff distance, basically what I showed you before. The magnetopause, as the conductance goes up, the standoff distance goes down, and it goes quite dramatically. This is between 1 and 2 RE, I mean, difference here, at times. You can also look at the reconnection rate, and we calculate that with the Bern-Hesse-Forbes method, I mean, by calculating this pseudo potential when you integrate along field lines. And so the reconnection rates also change, but not really so systematically. But one thing you see is that when you have low, I mean, very high precipitation and high conductance, I mean, there is not much spikiness. It's pretty much flat. And for lower precipitation and lower conductance in the ionosphere, you get these spikes, which are basically substorms, I mean, this is the global reconnection, so that includes the night side. Okay. Also fairly recently, this was work by Doug Kramer here in my group. So looking at bursty bulk flows and bubbles, those are injections into the inner magnetosphere. And I'll show you a movie a little later. So what he did is, so first of all, this requires a fully coupled model with the RCM. Otherwise, you don't get things right, I mean, in the inner magnetosphere. And so here is a snake plot. So this is time on the x-axis. This is magnetic local time on the y-axis. So this is just the night side hemisphere here. So this is midnight in the middle. Now the color coding is the peaks of velocity, of earthward velocity. So you get these flow channels that go to the Earth. And so their velocity is here given as a color code. And then the dots here are minima of the plasma entropy. So this has been a conjecture for a long time that these flows, these bursty bulk flows, are actually regions of low entropy because reconnection cuts off part of the flux tube and removes entropy from the flux tube. And so this basically confirms that. You see these minima of entropy very, very closely follow these fastest flows. Not always. There's some exceptions, but for the most part they do. And the other thing you see is that these bubbles eventually, I mean, this is a storm actually. So this is fairly high. Well, actually not. This is fairly, this is fairly quiet time. So the IMFBZ is rather around 0, maybe -10 at some point, but the bubbles have to go around the Earth at some point, so they always go away from midnight towards the flanks. So then you do statistics on that, you find that these bubbles, that about 80% of the plasma transport is due to the bubbles. That's this figure here on the upper right, so that's the percentage of plasma that is transported by bubbles. And the different curves are just different storms, the different events. And the little dotted one here, that is a quiet time. So the quiet time is a little bit different, but still further out beyond eta Re, it's 80%, over 80%, that's really transported by the bubbles. And as you come closer and closer to the Earth, around 4, so eventually the bubbles sort of slow down, and everything becomes more uniform convection. And here's the velocity of the bubbles. They're for different storms, it's different. But it all goes down to basically 0 right around 4 Re. So the injections come and eventually they will be stopped. And the final thing that I have here, this is Bashi's work recently, is so we can actually, there's so much in here. I can talk a whole hour about that. So what she did was take these fast flows in the tail. So you look at the equatorial plane here. The color coding is earthward velocity, but on a log scale, so we can also see small flows. And you see these earthward flows, and they're numbered here. And then you look in the ionosphere, and in the ionosphere, you can, and that's 2 different projections. This is just latitude versus magnetic local time. This is the polar projection. And you can actually associate each of these flows, with little bursts of aurora or precipitation that actually goes into the ionosphere. And I'll show you a movie next. That will pretty much be the last. Now, when you take a cut along a meridian here, so along a given magnetic local time, that's what's actually done in experiments. In Canada and other places, you have these, what they call the meridian scanning photometers, you can actually see how the aurora is moving north-south, and you see substorms, and this is a typical substorm thing. You see aurora, quiet aurora moving southward. Okay, so this is latitude, and this is different magnetic local times, so different panels. So it's latitude versus time here, and the color coding is the energy, the precipitation flux, energy flux, and you see at some point here, it all of a sudden it lights up. First it goes southward, and then it lights up. And then that lighting up actually propagates westward, and also eastward eventually. So it's a typical substorm, So this event is a substorm, and here we can see the whole thing as a movie. So the event starts out as quiet and becomes a substorm, essentially one big BBF. You will see that at about 2:30. About 1 hour into this movie, and well, it does take 1 hour. It's faster than that. But then it will not recover, becomes an SMC because the IMF stays southward. So that paper is in revision. So yeah, you see these flows happening all the time. So there's, always at the edges of the flows, there's reconnection happening. So this is still pretty quiet, so you see more or less quiet aurora. And then all of a sudden you will see this gigantic BBF coming in, and that's roughly now. So you see this real big guy coming in, boom. And you see the aurora expanding, it expands northward. It also starts expanding westward, typical substorm thing. Now, we don't have numbers in here because things are changing very quickly. But if you stare at this long enough, you will see a lot of intensification at the poleward boundary, and then you will see how they propagate southward or equatorward. And these are very well known from observations. They're called PBIs when they happen at the boundary, poleward boundary intensifications. And they're called streamers when they actually go southward, so these streamers. So I think I'll stop here and I go to my conclusions because it is time. Am I right? Yeah. I'll give you a summary and I'll give you not really conclusions, but some final thought. So we have come a long way. That modeling thing started in the early 80s, so we're about 40 years in, which isn't as much as the atmospheric community does, they're about 80 years in. Thanks God, computational constraints are not so much of an issue anymore because that used to be really big. It was really difficult to do these runs. Right now it's fairly easy. I showed you that the coupling with the ionosphere-thermosphere system is really critical. That really controls how things happening in the magnetosphere. This was first demonstrated actually by Joel Feder in the late 80s, and people didn't really believe him, but I think this is very well established here. And you can compare that to atmosphere models, that, I mean, whether it's weather forecasting or climate forecasting or whatnot. I mean, if you don't couple it with an ocean and cryosphere biosphere model, you don't never get the right answer. So, but the MI coupling that we do is still very primitive. I mean, there's a lot of work that needs to be done on that. I mean, unfortunately, it's a very complex thing. It's not easy to do. So yeah, we got a lot of things right, when you compare it with simulations, in particular, I think Reconnection and MHD models fits observations quite well. I mean, when you look at the observations of FTEs, I mean, a lot of stuff I haven't shown you, that actually really matches the observations. But I mean, the results need to be interpreted with caution due to limited physics. I mean, resolution is never good enough, and the numerical effect. So one shouldn't take the results blindly. One needs to understand what one is doing. Well, it's the same with experiments. If you don't understand if you don't understand the limitations of the experiment, you will also draw wrong conclusions. Now, the final thought is, numerical diffusion is always considered a bad thing. Okay, so we having lots of arguments between modelers, which model is more diffusive than another and whatnot. But I think the experience with the inherently diffusive models, I mean, actually may indicate something about the magnetosphere itself, because that what we call the collisionist plasma of the magnetosphere is not quite that collisionless. It's not quite that ideal. And that may be due to turbulence. I mean, nobody really knows, I mean, what the turbulent terms are. For example, in the tail, I mean, if you look at the tail plasma sheet, it's turbulent plasma. The magnetosphere sheet is turbulent plasma, a lot of turbulent plasma there. And so in some sense, I think MHD models, we may be in some sort of a golden zone where the numerical imperfections are actually mimicking the real dissipative and non-ideal processes. So in other words, if we drive resolution even higher, we make it less diffusive, we might not get better solutions necessarily. We may actually run into some issues now, I mean, because there is not enough diffusion in there. Okay, that's what I want to end with. And yeah, thank you very much. Thanks all for coming virtually. And I think there will be some questions, right? I mean, but that's up to the convener here, right? Okay, so I think I stopped. No, I should not stop sharing, right? Because we might go back to slides.
Yeah, best leaves the slides on just in case we go back.
Yeah, right. Okay.
Thanks for a wonderful talk, Jimmy. That was really informative and really clear. And we do have about half a dozen questions. So I'll read out the questions for you and who asked them. So our first question comes from Jason Durr. Is there a simple way to embed local regions which are best modeled kinetically within a larger global space, which is modeled using MHD?
Well, the Michigan group is doing that. Okay, so over the past years, Gabor Toth has actually embedded a PIC code into their MHD code. And obviously it puts it where he thinks it's important, like at the magnetopause, and I think also in the tail sometimes. This has been tried for a long time, believe me. It is very difficult to do because you have to match different time and spatial scales, at the boundaries and all that. So, and I must say, I haven't really looked into details, so I think it would be the right question to ask Gabor. I mean, he can certainly tell you much more about that.
Okay, excellent. Thanks. I'll pass that on.
But I should say it's not easy. It is not easy. It is, I mean, on many different levels. I mean, a computational level, but also on a level of understanding the physics, right?
Yeah. So our second question comes from Muhammad Shamir. He asks, what are the possible sources of the parallel electric field during reconnection?
Well, that's what MMS is all about. Okay, so I think that, I don't know whether he actually was in last week. I mean, Jim Drake talked about reconnection and about all those sources, right? I mean, you can write down a generalized Ohm's law that really applies, so, and the major terms are, if you have no collisions, you don't have resistivity in there. So you only have a term that is proportional to the inertia of the electrons, generally considered small because the electrons don't have much mass. And a term that is, and that the people think is probably the dominant term now, is the divergence of the pressure tensor of the electrons. So of course, that only comes into play if the electrons are really not gyrotropic. They're not even gyrotropic, you know. So MMS is the first spacecraft that ever was able to measure distribution function, electron distribution function, and they do see there is a divergence of that. Well, okay, be careful. There is the pressure tensor. I mean, they find definitely that the distribution functions are not nice Maxwellian, but they can measure that. But measuring a tensor or the divergence of a tensor is a whole different thing, you know. So I don't think they're able to do that. So yeah, that's the collisionless terms. And then there is an older theory that goes back to the 80s and 90s, where people looked at what they call anomalous resistivity. So in other words, that is a resistivity that is caused by waves, kinetic waves. I mean, the wave that people mostly looked at, I mean, was drift waves, because you have very strong gradients there. So you can see the drift waves, you know, and then you can do quasi-linear theory and derive a resistivity term from that. Now, what is the evidence for that? There is a bunch of papers from Cindy Cattell from using, I don't know, I think it was empty data and also icy data. So it's pretty old. It's 30 years old, 30 years old, where she actually did some estimates, you know, and she found out that anomalous resistivity, I mean, when you look, you have to measure the electric field and the waves in the electric field and all that. And she's estimated, I mean, quite high values of an anomalous resistivity. So that, I think, is work that has to be redone with better data these days. I mean, with MMS clearly has better data for that. But I haven't seen anything in the literature. But I must also admit I'm really not following that literature very closely. So that's my answer. So those are the three things, you know, primarily resistivity, anomalous resistivity, divergence of electron pressure tensor, and possibly the inertia terms, I mean, associated with the electrons.
Great, thanks. And just to follow up, Jim's talk is on the YouTube channel now, if anyone wants to follow up last week's talk.
He went into that. I mean, I think he went into that in great detail. So yeah, should be looking at that.
So our next question comes from Patricia Rafe. How does the ionospheric conductivity affect the maximum cross-polar cap potential?
Well, it's pretty simple, Pat. If it's infinite, it's zero. If it's infinite, it's zero. If the ionosphere conductance was infinite, I mean, the potential would be zero. As a consequence, the electric field would be zero, and as a consequence, the magnetic field line would be tied to the ionosphere. That's it. So there's virtually no limit, I mean, to which it can affect, you know. So we know the upper and lower limits. Now, how that dependence is in between, I mean, a lot of people have tried to address that, you know. I mean, you can also phrase it in a different way, or people have phrased it in a different way. Is the magnetosphere a current generator or a voltage generator? And there is no clear answer to that, you know. So sometimes it seems to be more like a voltage generator. So in other words, if the solar wind electric field doubles, you know, then the field line currents double. You know, that is sometimes the case, but not always the case. So I don't know whether that really answers the question, but it's an old topic, and I don't think it's fully solved.
So our next question comes from Debendu Sir. Is the polar cap index a good indicator of particle precipitation?
Oh, okay. Polar cap index, I think it's based on a couple magnetometers only that are on the polar cap, right? And I don't think that is even well correlated with precipitation. I don't think so. No, I don't think so. It's a totally different thing. I mean, it has been shown. I mean, I remember that was quite a while ago by Jeff Hughes, you know, who ran these magnetometers in the polar cap. I forgot the name of the chain, and he showed that these magnetometers react almost instantly to changes in the IMF. You know, and the IMF rotates. You know, I mean, a couple of minutes later, his magnetometers in the polar cap started to rotate, you know. So what they really measure is basically the solar wind input at some point, you know, but not directly the precipitation. I don't think so.
Yeah. Our next question is from Sergey. What is the best variable, field line currents or electron flux, that you get in MHD to compare with the aurora?
Ooh, okay, now yeah, that's a curveball, you know. I mean, FACs are not directly related to aurora, you know. I mean, and even the energy, well, the precipitation is definitely the better one to compare with the aurora, you know. But in general, if you want to compare with data, it's probably better right now. I mean, we have ampere. I mean, to compare with ampere. I mean, that's pretty high quality field line current data, you know, now that they have a high enough cadence. Precipitation data are actually hard to come by. I mean, there is, of course, there's DMSP, they measure that, and the old POSE satellites, but you're not really in the right location most of the time. You know, the DMSPs, they're mostly an orbit that goes along the terminator, so east-west, you know, so they virtually never fly through the night side, really. I mean, well, they fly through the night side, but never through, let's say, midnight, you know. So that is difficult, you know. So we don't have so good precipitation data, actually.
Yeah, so I think this next question follows up and is similar. In Bashi's work, which you showed as the last example, what was shown in the plots when you mapped it down to the ionosphere?
Oh, we mapped, I mean, first of all, I mean, we have a self-consistent ionosphere model, right? So if there's some field line current generated in the magnetosphere, you know, I mean, we should see that in the ionosphere. The problem is you don't see that at very small scales because the field lines converge very quickly from the magnetosphere to the ionosphere, you know, and eventually there isn't enough resolution that the code itself can follow that. So what we did was really just mapping along field lines. Okay, so we took the field lines from the MHD. We went out. I mean, basically, you take a point in the ionosphere, you go out in the magnetosphere, look what is the farthest point, where does it cross the plasma sheet, you know, and then you pick up all kinds of variables that you can find there, you know, and map them to the ionosphere, and then where do I really see something, you know? And it turned out that the velocity, the earthward velocity, was very good, so you could see things that looked similar, you know. So now that doesn't tell you really what the physical process is that actually makes the precipitation. Okay. So, I mean, there's certainly field line currents, but it could also be scattering of particles. It could be a lot of things that happen there, you know. So, I mean, all we can establish, you know, is the geometric coincidence, you know, between the mapping, I mean, between the tail and the ionosphere. And it really looks like like streamers and PBIs.
Yeah, it's a quite cool movie.
Yeah.
So we have one more question, I believe. This is from Antonova. Is it possible to include turbulence in turbulent transport in MHD-like models?
Yes. Yeah, no, of course one could do that. I mean, one way to do it, I mean, would be by parameterization. So in other words, I mean, if there's a good theoretical understanding or other kind of numerical model, you know, that actually tells me, I mean, what the diffusion coefficients are as a function of other parameters, you know, then one can put that in. Or if I want to do that self-consistently, one has to do a very high resolution. So we are not quite there yet. I think the people at UCLA have tried. I think Mustafa Al-Alawi has tried to do that, and Ray Walker. They have tried to do that with an MHD model, and so they got a little bit or a small part of the cascade. You know, so I think they got about 1 order of magnitude or 1.5 order of magnitude in the turbulent cascade. You know, I mean in K space, which is sort of the beginning. You know, but I don't think that would be sufficient. I mean, one would have to go probably 2 or 3 or 4 orders of magnitude. You know, so which would require quite a bit of computer power. Now there are people who do this actually with local simulations. I forgot their names. They're at the University of Wisconsin. I mean, they're theorists at the University of Wisconsin, and I've actually run box models of reconnection, you know, by and putting in a lot of self-consistent, or I don't know exactly how they did it, but they made the current sheets break up in a way that the current sheets became very turbulent. And so yeah, so one can go along that way, definitely, you know. So it's something to consider in the future. Yeah, definitely.
Okay, excellent. That's all of our questions today. Thank you for a great talk, Jimmy.
Well, thank you for your praise here.